This audio slide presents our work about theory of evidence for face detection and tracking published in 2012. Here is an overview of the context. The goal is to automatically track the face of a person moving in front of a camera. The method works in two steps: face detection based on belief functions, then probabilistic face tracking based on particle filtering. The process takes control of the camera, pan, tilt and zoom to keep the face in the center of the image. An elliptical region of interest, including the face, is estimated in real time. The field of application is broad. There is of course audiovisual communication, like video conference with high quality of service, but also human-machine interface, robotics, video surveillance and CCTV, biometrics and recognition, face expression analysis, or even online games, animation movies and augmented reality. This pyramid illustrates the two ways for processing data. Deduction is commonly used. It means starting from a generic face model, go down and deduce, by comparison with pixels, where the face is in the image. One can also work in the opposite direction, namely make induction. From low pixel data, including prior context, we get some primitives like color or edges, then compute estimates like position or size. From those measurements, we put labels onto pixels, like background or region of interest, and finally go up towards interpretation and decision about the face. Here we combine both ways: low-level vision to get skin color pixels and high-level detector to get a rectangular bounding box of the face shape. Then the key point is the fusion of these two information sources. This block diagram illustrates the main idea of the paper. Instead of using a huge database with many faces and complex algorithms like active shape models to infer the face, we use a simple procedure with few data and simple initialization step by the user. So it is a semi-supervised algorithm which handles a priori context information and low-level data like color in order to account for the variability, noise, background, clutter, and morphology of the face. Then, a transferable belief model tuned with proper parameters yields the region of interest, possibly with artifacts and occlusions. This is the entry of a tracker that estimates in real time the location, pose and size of the face, so that the deformable moving object may be tracked at video rate. Face modeling uses evidence theory to choose between two hypotheses: face class and background class. We use a quick initial step for learning the two classes. The user selects manually a zone containing the face in the first image of the video sequence. This rough selection yields the prior model for skin and background. Then, face detection is based on two information sources. First, the chrominances in order to detect skin hue. Pixel color is modeled with a priori mask set. Second, the well-known Violet-Jones face detector gives a bounding box. A belief function is assigned to each pixel according to its position with respect to this bounding box. For a robust fusion of information, we need a compromise between precision, source reliability, and conflict. Since color sources are dependent, we implement a cautious rule to merge the color mask sets. In order to avoid false detection, we adaptively tune the Violet-Jones masses thanks to a feedback loop taking into account the conflict inside the bounding box. To get an output compatible with the probabilistic tracking, the mask functions are transformed into pygnistic probabilities. Face tracking is achieved with a classical probabilistic approach. Since the outer contour of the face is approximated by an ellipse, we use a particle filter that estimates the ellipse in two steps. First, it gives the center of the most informative ellipse. It means that matches the best the face hypothesis. To do so, the weight of each particle is computed as the sum of squared pygnistic probabilities inside each ellipse. Then, ellipse size and pose are adjusted by least squares fitting. We conducted both quantitative and qualitative evaluation. The ROC curves shown here yield a detection rate of about 80%. The average position error is about 20 pixel difference between ground truth and estimated location of the face. As regards qualitative evaluation, we get good tracking even in variable lighting and changing of pose or distance to the camera, as shown in the video sequence here. Concerning limitations, we have to mention that it is a semi-supervised method with some ad hoc parameters that are tuned at the beginning of the process, and it is actually limited to indoor applications. Thank you for listening and enjoy the reading of our paper.